right, this is lesson 3.3. We are working with some properties of logarithms. Here's a quick warm-up. Try them. Pause the video, see if you get the right answer. Okay, first, kind of like another property of logarithms, we have our change of base, which allows us to evaluate log base anything using common logs and natural logs. And we would use this more so if we had a calculator that didn't allow us to do the log of any base. Okay, we can do the log of the value of like the bigger number divided by the log of the base using common logs, base 10, or natural logs, base e, and we'll get the same answers as so. Okay, good. So, an example of this. If I want to rewrite log base 5 of 16 using common logs, that's base 10. That would be the log of 16 over or divided by the log of 5. We just did that math. We got 1.722. Dot, dot, dot. So remember, this is really asking you 5 to what power gives you 16? To this power. 5 to the 1.7227 would give us 16. Okay, rewriting this as a ratio of natural logs. We can do the same thing using log base e, natural log. The natural log of the value of the bigger text number, 16, divided by the natural log of the base. And we can see we'd get that same answer like I just showed you on the graphing calculator. Okay. This works for variables too, and today we're going to use log properties with ones that have variables. Obviously, we can't actually evaluate this one because we don't know what x is, but I could still write it using my change of base formula as a ratio of common logs. Log of x, that's my value, and think base always goes on the bottom, base on the bottom, divided by the log of 2.6 would allow us to evaluate that for any x value. Writing as a ratio of natural logs, same thing. Okay. That's the change of base, folks. Again, said this a couple times, but you won't use it a whole lot because your graphing calculator can do this operation. If you ever get a scientific calculator and you need to evaluate log base 5 to 16, you can use this change of base to figure out 5 to what power gives you 16. Okay, that's kind of the first property we're going to talk about. Oh, gosh. We have a little proof for the next. It's not bad.
No.
Okay, it's an algebraic proof. It's not bad. You don't have to like label out. It's not like a 2-column proof where you have to say like, oh, we could do this because of this. We're just gonna do like the algebra, okay? No, this is just an appreciation for where these properties come from.
Okay.
It's good for the brain. All right. So they're saying let x be log base b of n and let y be log base b of n. The first thing we're going to do is we're going to rewrite these, and this is on your quiz, rewrite these in exponential form. All right, so this in exponential form would be b to the power of x is n. Okay? So basically what we're going to do is we're going to convert these to exponential forms, do some math with exponents because we know all those properties, and then convert them back to logs to discover the log properties. All right, let's do the same thing with this one. This in exponential form would be b to the power of y is n. All right, so what happens if I were to take m times n? Again, we know how to do this operation with exponents. So m is the same as b to the x. So I'm going to do b to the x times n is the same as b to the y. All right, exponent properties. When you have the same base, in this case we do base b, and you multiply them together, what operations do you do with the powers?
Addition.
Add them, right? So I know that that's the same as base b to the x plus y. Now m times n I'm just going to write as mn over here. All right, we know how to do this with exponents. Let's convert this now back to a log. So I have an equation in logarithmic form, or I have an equation in exponential form. If I want to write it in logarithmic form, I'm going to start with writing log base what? B of mn. Remember, log, it always equals your exponent. X plus y, yep. All right, if we go back to the original step here, it says x is the same as log base b of m, so we're going to do a little substitution in there. And y is the same as log base b of n. So here's your first property you just proved. That the log of any base, that's what base b is kind of standing for here, of a product of m times n of any two factors is the same as taking the log of each factor and adding them, and it really stems from the exponent properties because logs are powers. Logs are powers. So when you multiply the values, you're really just adding the exponents. Okay, so this is called the product property. We'll write this in our notes later on. But that's a product property. Proof done. Okay, second proof. And I'm really sorry, I only have fun proofs for 2 of the 3 properties. The other one I'm just going to tell you because there's no fun proof for it. The proof is not that great. So we'll only do 2 of them. Okay, same steps here. We're going to write these in exponential form. So b to the x equals m and b to the y equals n. Okay, but this time I'm going to prove to you the quotient property. So instead of timesing m times n, we're going to divide them. M divided by n. Okay, so we have m, which is b to the power of x, divided by n, which is b to the power y. Okay, exponent properties. I have the same base. What operation to do with powers? Subtract them. Okay, I think you can probably see where this is leading to. So that's the same as b to the x minus y. Okay, now we're going to convert this to log form. So I have log base b of m over n is the same as x minus y, or equals x minus y equals the power. And then we'll go back, substitute in what x and y were originally, which was log base b of m, log base b of n. Okay, here's your quotient property. And again, this stems from exponent properties because of the relationship between exponents and logs. But if I have a log of a quotient, that's the same as subtracting the logs of each, your numerator and your denominator. Okay, your quotient and your dividend and your divisor, if you want to think of it as a quotient. Okay, there's your quotient property.
That was so fun.
Thanks, I thought so too. All right, so here's the 3 properties you got to know. This is the first one we proved, and I'm going to use the same, your book uses a little bit different letters. They use log base A. I don't know why. I've always ever seen B as like base, but it's okay. Log base A, and then for their like products, they use U times V. We're going to use this property 2 ways. We might use it to take a product like this and break it up into 2 logarithms. And we would add these powers. Or you might use it the other way. You might use it to kind of like simplify. If you have 2 separate logs that are being added together, you might put them together in 1 log by multiplying the u and the v, whatever the argument is, whatever you're taking the log of. It depends on the problem. So use this property like both ways. To go from here to here and from here to here. All right, quotient property. Quotient property is the other one you proved. So if you have u divided by v, we would take the numerator, and you always subtract the one that you're dividing by, because obviously subtraction, the order matters. So this one down there should always be your denominator. All right, here's the one where I don't have a fun proof for. But we can like kind of talk about it. If I had a power, what is your book? It's u. This is technically a power, right? A to what power gives you u? If I have a power raised to another power, think about it with exponents. What operations do you do with the powers? Multiply them. Yep. So this is the same as taking this power of n times this power, which is log base a of u. So that's technically a power. A to what power gives me u? I always think of it as you kind of just bring that power out in front and multiply it. So power to the power you multiply. Okay, one little caution note that I see students do that I want to warn you not to do. This is a non-example. Caution. If you have the log of like a sum, that is not the same as like distributing, if you will. You can't do that. The only way we could separate these with addition is if this was like a product. If we had like x times 3, then we could separate them and do the log of x plus the log of 3. That's like, people try to use the product property on like a sum. Okay, that doesn't work, and you can't distribute logs. No. Don't be that person.
I should be that person.
I'll call you out if you're that person.
I'm already calling out anyway.
Okay, what do you got? 5 minutes?
I said something.
Let's try a couple problems. All right, so we're going to use some of these log properties.
Oh.
And here they want us to write each logarithms in terms of the natural log of 2 and the natural log of 3. So here are the natural log of 6. You kind of have to like ask yourself, how can I rewrite 6 in terms of 2 and 3? 3 times 2 or 2 times 3, right? We all agree that the natural log of 6 is the same as the natural log of 3 times 2. So I have a product here. So I can use my product property that if I have the natural log of 3 as a factor times 2, I could separate that as a natural log of the first factor, the natural log of the second factor, and we'd add those. Yep, because it's product. That'd be our answer. Okay, a little step up here. I have 2 27ths, and I want to write that in terms of 2 and 3. Ideas.
2 divided by
3 to the third. I like it. Could you do 3 times 3 times 3? Yeah, you could. But now we'll get a little mix of both our power property and our quotient. Okay. So first, I see a quotient. And I'm like, okay, I can separate those. And since I have a quotient, what operation would I do with the logs? Minus. Yep. Think of exponent properties. If you're like really dividing those, you'd subtract the powers. And then we can do this one step further. I have a power to a power, so you can kind of bring that power in front or multiply those, the natural log. And the reason why we bring it out in front is because you'll more commonly see this written as 3 ln 3 instead of this. You won't ever see this. Because then we get confused on, hey, is this a natural log of 9 or is this the natural log of 3 times 3? Okay, so a lot of times too, you might see me kind of do something like this to show you like, hey, in my argument, I'm actually taking the log of 9. So that's why we bring it out in front. Isn't that kind of fun?
Yes.
All right, now these ones are kind of similar. We've actually like obviously done ones like number 1 before. Number 2 we haven't, so we'll kind of use a log property, and then 3 we'll use some log properties as well. This one's just a little bit more intense, and there's like kind of a couple ways you can do this. So first of all, when I see a radical, I would rewrite that as a power. So that's a 1/6 to the 1/3. Okay, and then we could bring that power like out in front. So that's the same as 1/3 times the log base 6 of 1/3. And we actually know what this is. Oh, did I say 1/3? Sorry. Log base 6 of 1/6. This is asking me 6 to what power is 1/6? -1. So this is -1 times 1/3. And we end up getting -1/3. So we can kind of use log properties. Okay, we'll do one more and then we'll save 3 for tomorrow. Okay, here I'm going to use the log property kind of backwards. Here I see I have this like expanded version. These rules also apply for natural log. Obviously, this is log any base, so log base E works for this as well. I forgot to say that. These work for natural logs too, okay? Here I see I have 2 separate natural logs. Now, there's obviously a couple ways you could do this. If you're like starting to cancel things, that's fine, but let's use log properties here. That I could rewrite this as a natural log of, and since I'm adding these together, I'd multiply the insides, add the exponents, so you get natural log of e to the 7th, which that's just 7, or that's asking you e to what power gives you e to the 7th. Now, obviously, I know you could have done this. 2 plus 5 is also 7th, but this uses like our log properties the other way. All right. We'll stop her there. We have a little short in class periods today. We'll finish this fun lesson tomorrow.